Okay, well, before we start, we'll do a short introduction and then I will hand over the floor, okay? I think we can start, and then there will people still be joining us. Okay, let's start. So, hello everyone, and welcome to our last talk in this year in our webinar series. Today we have the pleasure of having Dr. Richard Kron from the University of Chicago and the Fermilab, and also he is currently the director of the Dark Energy Survey. Among his studies, Dr. Kron specializes in galactic and extragalactic astronomy and astrophysics, focusing his studies on distant galaxies and quasars using survey techniques. And today he joined us to talk about the latest news on the Dark Energy Survey. Before we start, a quick reminder, this webinar is also being streamed live on YouTube. You can find the link on our website, or you can access it on our YouTube channel, LIneA MCTI. Dr. Kron, thank you very much for being with us today. The floor is yours.
All right. Well, thank you very much, Rodrigo, for your hospitality. It's always fun to talk about this project, and I do appreciate the invitation. So let me show my screen. There we go. And I understand we should have questions. We can be informal about this, but I won't be watching the chat or anything like that. So if somebody wants to ask a question, please just speak up. So I also I realize that many of you are very familiar with the Dark Energy Survey. You're working on it as a primary project, perhaps, and so some of this will be fairly elementary. But I hope that at some point I can tell you something that maybe you hadn't quite appreciated before. So let's get started. So this is a rough outline of some things I wanted to talk about, just a bit of the background, where we are in the project. I'll talk in very broad terms about the data, and then give some examples of work in cosmology and astrophysics, and then just have one slide on the legacy of the project, or where we go next. So this is starting in a little bit from the U.S. perspective of how things get funded. So this is the project is like other projects, like the Rubin Observatory or LSST. That's a joint project from the U.S. perspective between the funding agencies of the of the Department of Energy and the National Science Foundation. So with respect to the Department of Energy, they are focused on a particular set of physics themes, which does include dark matter, measuring the neutrino mass, inflation, and dark energy. So it's a fairly specific set of science topics that the Department of Energy will provide funding for. And the NSF is more is broader than that, but it does include cosmology. So there are a number of, as I mentioned before, joint projects between where both of these agencies that typically have different constituents, high energy physics being with the Department of Energy and astronomy being with the NSF. They've come together in a productive way to fund these projects, and it's started with the SDSS in a couple of decades ago. So I'm not sure you're familiar with this article that I have here of Simon White. It was published in 2007, and it's an interesting discussion about the cultures of the high energy physics community and the astronomy community. And he's asking the provocative question of whether dark energy is really a healthy thing for the astronomy community. And you don't have to agree with his arguments, but it's a very interesting read. And he talks about, his sort of points have to do with whether one big project where a lot of resources go into some major experiment that answers some admittedly very important and very intriguing scientific question, whether that's necessarily the most cost-effective way of spending money or spending resources such as people. So I think one of the things he's arguing is that especially for career advancement, it may be better for younger people entering the field of astronomy and astrophysics to have smaller projects that they can develop and take more leadership in at an early stage. So I hope I remember to come back to this at the end. I want to make a few remarks about that. But for now, let's just say that this argument was made in 2007, and it would be interesting to revisit the argument now with the passage of time. And this is the last thing on this slide is just a bit of an advertisement. There's a World Scientific book that was assembled by many people in the project. There were many chapters with different authors that give sort of a full accounting of the history of the project. And it's something, it's a rather unique thing that a scientific project like this would have a whole book published about it. Okay, so let me start here with a few remarks about the hardware, about the telescope itself. So in the telescope design in the 1970s and in this century are completely different. In the 1970s, you did not have computer control of things at anything like the same level we have it now. And so what you had to do is build extremely heavy, rigid structures out of steel that would have very minimal flexing. And today you can build very lightweight telescopes that are much less expensive because they're lightweight. So you have a strong motivation to do this. And they are flexible, but you can correct for errors using sensors and feedback loops that are controlled by computers. So there's a very different design philosophy. So the telescopes that the national observatories, one in Chile at Cerro Tololo and one in Arizona at Kitt Peak, had sort of a legacy of these large telescopes for which the future was not clear, given the existence of 8-meter telescopes and so forth. But it turned out fortuitously that there was a perfect match between the capabilities of these old telescopes and what was needed for cosmological surveys. And that is, you wanted to put something at the prime focus. In the case of the Blanco telescope here, it's the dark energy camera. And in the case of the Mayall telescope, it's the DESI spectroscopic instrument. And both of those things are very massive instruments. And so you have to have a big, strong telescope to put anything there at the prime focus. So here was this wonderful match of a facility that was looking for something to do, and then a scientific rationale for saying, oh, we need to work on dark energy, we need a wide field camera, and the wide field camera is going to be really big, so we have to put it on your telescope. So that was sort of the way the story went. And the early sort of way that the project came together was about the construction of both the camera and the software to run the camera, and money that the founding partners, including the DES Brazil group, were contributing to this effort in one way or another. And then the partnership now, of course, is well beyond the construction phase. So this is a kind of a classic picture of the site in Chile. It's not quite in the as far north as the Atacama, but it's well north of Santiago, and the Blanco Dome is the large dome. And as I have already alluded to, the national observatories were having sort of an existential crisis at some point about what was their purpose. And the dark energy camera has now really breathed new life into this observatory. It's an extremely popular instrument for the community, the astronomical community, which of course is an international community, not just the U.S. So just one fun picture here. So I had the experience of being present on the mountaintop at the beginning of the year one observing season. And so this is a picture that was taken of the group in the control room at the Blanco, celebrating capturing the first image. So this is a little bit of an exaggeration because before the year one, there was a science verification period, and quite a few of those exposures are actually part of our data. So it's not exactly fair, but you get the idea. So this is what it looks like. And you can go to the observatory and actually never see the telescope. You could, this is at the ground floor, and you can spend the entire time in the ground floor watching things like Quick Reduce, which was one of the DES Brazil contributed pieces of the experiment. Here's what you see when you're observing at night. Every exposure consists of many CCDs worth of information covering a field of view of over 2 degrees in 1 dimension. That's an astonishingly large field, given the size of given the image quality. So it's excellent image quality, very uniform image quality over a very wide field. So a little bit more about the sort of the background of how to think about this. So here is a map that was created by counting galaxies by eye on photographic plates that were taken as part of an astrometric program at the Lick Observatory. And the catalog was published in 1967 as a exploratory effort. The Coma cluster of galaxies is this bright spot here in the middle. And this sharp edge on the right-hand side is the declination limit of the observatory. But basically, this is most of the northern hemisphere above the Milky Way. So you get a sense of how many degrees across this would be. It's roughly, it's a steradian across the image here at least. And you can see the filamentary structure very clearly here. And it's when you measure the redshift for this, you get a sense of the actual physical dimensions. You can determine that the structure is too large to have been actually assembled by gravity. And this is what it makes it so scientifically exciting. It's that there must be something that imprinted the structure early on, and sort of that is cosmology. A simple way to put it. So this became a very compelling scientific field, especially later in the 1970s, with the recognition of what I just said about the fact that there's something going on here which is more than gravity. So this is actually kind of an old story. Okay, all right. Well, let me go through this in order. So to get this large scale structure, we have to measure things over very wide fields of view. And so that changed. So instead of thinking of things like the Hubble Space Telescope, which has a tiny field of view, or the extremely large telescopes have very tiny fields of view, there's this other branch of thinking, well, we have to build telescopes with very wide fields of view because there's structure here and that's the only way to sample it. So that's what may seem like a modern scientific direction but actually it goes way back. The Herschels constructed a map of the sky based on visual observations in the early part of the 19th century. And that has become the famous NGC catalog. The NGC is essentially 90% of the objects in that catalog come from the Herschel's observations visually, both in the Northern Hemisphere and from the Cape of Good Hope. And then this catalog was assembled into maps that are like this one. And these, you might think that visual observations would be difficult to calibrate, sort of different observers at different times with different equipment would do not a very good job of uniformity. But in the case of the Herschels, they did a remarkably good job of the uniformity. That was their intent, was to make a uniform catalog. And if you were to plot modern photometry of these of galaxies of the same general magnitude, you would find very similar structures. So what you can see on the left is the local supercluster, which is this kind of goes up and down, and on the right, sort of, I don't know if you can see my cursor, but this here is the Perseus Pisces supercluster. So this is large scale structure, which was known in 1869, I think is when this map was made, and it was commented by people like Alexander von Humboldt, and who was a German explorer. Herbert Spencer was an English philosopher. All of these people had something to say about this large scale, what we now call large scale structure, but at the time it was known to be a remarkable feature of the world, but it wasn't known what it was. So that's just for fun, and let's move on here. So the dark energy survey is part of a much bigger scheme. So the idea is to measure dark energy with increasing levels of precision and increasingly expensive equipment and increasingly longer amounts of time needed to do it. So we are, along with EBOS, our so-called stage 3. It's a more or less artificial designation that has to do with the constraint power of the experiment. And then coming along, our DESI, of course, which is starting operations, or has recently started operations, and then Rubin coming up. So the frontier, if you might want to call it that, is that with such incredibly large statistics, we need to reduce the systematic errors. Okay, let's see. Right, and so this statement here: the cosmology objectives drives the specification. That's a bit of an exaggeration for Rubin LSST, where other types of science have definitely influenced the cadence of the observations and things. But as a rough approximation for SDSS, for DES, it was certainly the case that the cosmology constraints said these are the specifications for the experiment, and then the other science comes about as it can. So a little bit about the data. So here is a picture that shows the footprint of the DES on top of, I think that's the Gaia catalog, I'm not sure. Down at the bottom are the Magellanic Clouds, and we stay away from the Magellanic Clouds because we don't want the stellar contamination. Up at the top is the overlap with the Sloan equatorial stripe, which gives a calibration. And then the strange look to it has to do with trying to overlap with the South Pole Telescope field of view and VISTA field of view. And then there's some filling in. So it's a kind of an oddly shaped thing, but that's what we've got to work with. And so within this 5,000 square degrees, The most recent compilation, which is what we call DR2, a public release, has almost 700 million objects, and with unbelievable precision for both in the photometry and in the astrometry. So quite a remarkable achievement on its own. And then the reason I'm going backwards here and talking about the first 3 years of data is that's what has powered the cosmology results that I'm going to show in a bit. So that is a similar footprint, but not quite as deep as the full 6 years. And we are, the images and catalog data are being supplemented by additional data that are needed to reproduce what we published in the cosmology papers for the first 3 years. And that's a set of data, sort of value-added data that we call the Y3 Gold. And that will be made public next month if things go according to plan. Right, okay. So let me say a little bit about the deep field. So in addition to the 5,000 square degrees of the wide field that I just showed you, there are something like 10 what we call supernova fields, and they're supplemented by a few other places where we've gone back and repeatedly measured the same part of the sky over and over and over again. And these are, it was primarily for the detection of type 1A supernova. So the idea was that each of these 10 fields would be looked at no less than once every week. So I didn't write this down very well, but there's one visit per week, one pointing each week, and on that pointing you take several exposures through all of the filters, the GRIZ filters. So at the end of an observing season, you have many weeks worth of multiple exposures, and then you have 5 years of this. So there are only 5 observing seasons for the supernova. So that's so for the supernova, you look at the individual single epoch images, but then you can also take all of these images and add them up together and to get a super deep picture. And that's what we use for a number of types of calibrations for the wide field survey. And so for that, the COAD is of, so if you multiply 10 of these fields times 2.7 degrees, you get 27 square degrees. The COAD is only 5.9 square degrees. That's partly because we haven't finished this yet. So that number we hope will go up. But it's also because there's a lot of masking going on for dealing with artifacts. And also not all of the areas covered with the spectroscopic surveys, and not all of it is covered with the VISTA infrared survey. So the total amount of area that we're using for the calibration is a fair amount smaller than 27 square degrees. Anyway, it's amazing data. So just to show that without the text on top of it, here is 1 CCD worth of co-added data in a deep field. And then the next slide shows a zooming in of that. So just a few arc minutes on the side, and it just seems, I just find this very inspiring to look at this. Just one filter and nothing fancy. It's just what it is. Okay, so right. So just to acknowledge that the science server that is very much part of the data access tool for the collaboration and for the public. So this, of course, is something that is well known to LINEA, and it's something that is, it's a central part of what we need for doing the science. So a big thank you. What am I saying here? Okay, yeah, this is the news. Okay, so the news is that we're now starting the analysis of the full data set. Those of you in the project, of course, know that very well, but we've finished the analysis the first 3 years, pretty much, not completely, but pretty much, and we're ready to move on to the Y6 clustering and weak lensing constraints. So we're hoping to finish that. Sorry, I'm not being very clear. There's kind of layers of how this works. So the central layer is what we call it's the combination of a measurement of the clustering amplitude and the of the galaxy correlation, and the correlation of galaxies with a measurement of weak lensing, which can either be the correlation of the galaxy field with the shear field or the shear field itself. So that's what we call the 3x2 point analysis. That's because there are 3 correlation functions involved. And then there are other cosmological probes that we include on top of that, which include, for example, the supernova Hubble diagram, the measurement of the baryon acoustic oscillation scale, and the counts of rich clusters of galaxies. So those are that will happen separately and later. So we're hoping to wrap everything up in 2024 is the goal. So we're sort of gauging our funding profile with that in mind. And the other thing we're actually having discussions about now have to do with how this fits in with Rubin LSST timescale, in a sense that we want to make sure that we finish our work before people drift off to Rubin LSST. But if Rubin LSST is delayed, then we want to make sure that there's still interesting things to do with our set of data. So it's sort of an interesting discussion that we're having right now. Okay, this is a slide that I adopted from a presentation last May that I'll tell you about next. But it's just the whole point is to illustrate the complexity of the whole process, starting from the upper left where you have the original data coming in, and then over on the right you have the publications about the 3x2 point correlation cosmology. So everything in here is itself a complicated box having to do with measuring the shears, measuring the photometric redshifts, measuring the effects, the sort of systematic effects, and accounting for them, understanding the errors, and estimating the uncertainty on the errors. So it's this takes this, probably there were the number of people in the DES collaboration at any given time, since people come and they go, it's probably of the order of 300. Of those, maybe half of them are working on some aspect of this project. So roughly 150 people have contributed to one of these boxes, at least one of these boxes. So we had sort of a coordinated unveiling of the cosmology results last May, and that means that there were many papers that came into publication at the same time. And so on that occasion, we arranged a webinar, which is now on YouTube. And this was attended by 700 people. So it says testimony of the broad interest around the world in not just cosmology, but in what DES had to say. So this gives you just one slide from that webinar. And so trying to be fairly, just in simple terms, what was actually found. So the the cosmological parameters that are most strongly constrained by the DES 3x2 point approach happen to be the matter density omega m on the x-axis and the amplitude of clustering, which is the S8 parameter on the y-axis. So so many of the things that we show are sort of likelihood contours in this particular parameter space. So it's not to say the other parameters, the other cosmological parameters are not constrained, but these are the ones that we're focusing on. So the blue contours here are just the cosmic shear, and what that is a correlation of the shape of a distant galaxy with the shapes of neighboring galaxies. This how the correlation works as a function of angular scale by virtue of the fact that that the light from these more distant galaxies are being seen through a common screen of mass in the foreground. And of course, as the correlation gets lower as you go to larger angular scales. And then the orange line is the combination of the galaxy-galaxy clustering, which is the foreground sample, and the correlation of the shapes of more distant galaxies with those particular galaxies. That's the gamma. And so those are independent measurements, the orange and the blue. They are consistent with each other. And the gray contour is the combination of all three. So that's the gray contour is the main result from this analysis. So this result is better than the year one result because there's more area. And so we expected that, but it's actually because the methods we devised are also better, that the signal to noise was something like 20% better than you would expect just from area alone. This result is also consistent with other weak lensing studies and the particular values of the parameters, I should say. So the gray area, and also with the cosmic microwave background. And so that's a very significant statement because the cosmic microwave background is telling you about the amplitude of clustering at a redshift of 1,000 or very shortly after the Big Bang. And what we're measuring is something completely different. We're measuring the amplitude of clustering at recent epochs on large scales. And so if it's a testament that the lambda cold dark matter model is capable of describing the growth of structure over very different cosmic epochs, which is a very strong statement. Okay, so then another parameter is, well, sorry, on the left-hand side here, let's do this one at a time. We're adding in more constraints from other surveys. So the gray contour on the left is the same thing I just showed you. And the orange is other kinds of constraints at low redshift, meaning not the CMB. Low redshift means redshift of 1 and less or so. So those would include supernova Hubble diagrams. It would include baryon acoustic oscillation constraints. It would include redshift space distortions, all of that. And so the combination of the orange with us is the purple. And then the Planck is the green, and that's the high redshift constraint. And then the blue contours is everything combined. So these are all consistent with each other. And you can see that the blue contour is is pretty small at this point. It's shrunk down to so we're measuring things at the level of a few percent. So this is the dream of precision cosmology. When I was a graduate student, that would have been an oxymoron, that there was no such thing as precision cosmology, but now there is. So that's changed. And then on the right, you open up the parameter space by adding a parameter W, which is equation of state parameter in the event that the cosmological constant is not a constant. And you can see that it would be -1 in a cosmological constant universe, and you can see that the contours are consistent with -1 with relatively small error bars. Okay, then I'm just going to go through a few of the individual results that are in addition to the 3x2 point cosmology results. So this is a relatively recent paper on measuring the scale of the baryon acoustic oscillation. So this is a 2.7% precision. So this is the baryon acoustic oscillation is an angular scale that is apparent in either the power spectrum or the angular correlation function of galaxies that we call the lens galaxies, or I misspoke. This is a separately picked sample of 7 million galaxies that tend to be red type galaxies at a particular high redshift bin. And you can see the feature on the left plot, the bump, and that picks out a scale of something like 100, and just visually, it's a little bit more than 100 megaparsec scale. And so you ask, that is, how does that compare with what you would expect from the Planck measurement of the baryon acoustic peak? And that is related to that. If you were at the Planck level on the right-hand plot, you'd be at 1.00. But what's interesting here is to compare the dark energy survey result, which is the gold star with its 2.7% error, to other measurements at other redshifts. And so this looks a little bit low, but it's a sort of a 2 sigma away from the 1.00, and so no one is making extravagant claims for that yet. But later, when we get the full Y6 measurement, the error is expected to go down to 2%. And it's remarkable that this is all based on photometric redshifts, and it's still nevertheless is competitive with spectroscopic surveys at the high redshift end. Okay, then with respect to the type 1a supernovae, so we have something like 200 supernovae that have spectra of them, and so we can type the supernovae based on the spectra, many of which have been taken with by our Australian partners with the I guess it's no longer the Anglo-Australian telescope. But if you instead relax the criterion for selecting a supernova and just have the redshift of the host galaxy, then you can get something like thousands of supernovae that whose redshift and you know it's a supernova from the light curve, but the ambiguity has to do with the fact that it might be a core collapse supernova and not a type 1a supernova. So if you can get a grip on how well you can filter out the contaminating supernovae, and if you have a good model for dealing with the bias due to the imperfectness of your filter, then you can do cosmology with not 200 but 2,000 supernovae. So that's where that's the frontier of the supernova work now within the DES. So the picture shows the simulated survey, not the real data yet. But we do expect to see something like this in the fairly near future. I hope in the next few months. So the top is the Hubble diagram, and the bottom is the residuals. But the idea is that so there's a kind of a probability that the thing is a 1A, shaded in color on the right-hand side. And you can see that the things that are off the main trend are not colored dark red. So this is working. I think people are pretty happy about the way the analysis is going here, that we can take a sample that does have some contamination by core collapse supernovae and still do cosmology with it at high precision. And that precision is expected to I wrote it down here, about 4% on the W parameter once the supernovae are combined with things that have orthogonal constraints or complementary constraints, namely the low C sample and the cosmic microwave background. Okay, then this is another relatively recent result, but there's you can use the weak lensing, the shear field, to reconstruct a mass map, which is essentially closely related to the projection of mass, of foreground mass in front of the galaxies for which you have measured the shear field. So this is a map where the lighter colors means a higher surface density of mass. The darker color is the lower surface density of mass. And the little circles represent the rich clusters of galaxies. And you're supposed to imagine that that there's a correlation in the sense that where the mass map says there's more matter, indeed there are a larger number of rich clusters of galaxies. So that's a nice demonstration, and it's a consistency check, and as well as something that you can do science with. Okay, then here's something that some of you are familiar with. I think all of you are familiar with some of this, right? Okay, but so we have one of the things that has been apparent for quite a while is that these wide field surveys are extremely good at constraining properties of the halo of the Milky Way, especially finding new dwarf galaxies or ultra faint dwarf galaxies that may be in the process of being torn apart tidally by the Milky Way, or may in fact be extremely distant objects that have not yet fallen into the Milky Way. And also these streams, and the streams are related to the dwarf galaxies in that they are the tidal remnants of them, and they can be detected with a variety of fancy techniques of filtering on color and magnitude, and which I won't go into, but you can see that there are quite a few streams within the DES footprint. That's not because we were just lucky. It was because the data within the DES footprint are deeper and better, and therefore more capable of finding these streams than outside the footprint. So you follow these things up with spectroscopy, and the spectroscopy gives you the radial velocity. And since you can measure the proper motions with Gaia, then you have the full 6-dimensional phase space, as well as the metallicity, which you also get from the spectra. So there's this, again, it's a program that's largely using the Anglo-Australian telescope, which has been part of DES. But as you can see, there's a lot of data here that are not in the DES footprint. So I can't categorize this as a DES result. It's a combined result. But there's an amazing amount of information on that is based on dozens of spectra in each one of these streams. So what you get ultimately is a lot of information about how about the structure of the Milky Way halo, so how mass is distributed, and to what extent these. Essentially, what you can do is you can simulate what would happen if I took an object like a dwarf galaxy and threw it into a potential that looked like this, or had this kind of lumpiness in it, and then see whether you get consistent results. So I think this is a very active field, and of course it gets into dark matter as well. So here's another result that I think a number of you are very familiar with, which is about a census of the outer solar system. So the idea here is that the reflex of the Earth moving around the sun, as seen by some object at the distance of Neptune, is of the order of a couple of degrees. So as the Earth goes around the sun, something at the distance of Neptune would show a parallax of something like that, which is a good match to the field of view of the dark energy camera. So what this means is that by looking at multiple detections of objects that are moving in the outer solar system over a period of several seasons, and by being able to link and properly link that this is the same object observed at different weeks or months in the same season and on different seasons, you can actually do a very good job of discovering things that are in the outer solar system. So these are, this is just saying that 20% of all of the known TNOs, this is summing up, for years of very intense effort, have been discovered by the Dark Energy Survey, or in our particular data. So this paper has something like half of the 800 trans-Neptunian objects, and most of them are new to this, and it's newly reported in this paper. And with it, by characterizing your detection efficiency, you can do statistics with these. Okay, so what I'm showing you on the screen is a standard way of looking at what is in your catalog. The x-axis is the semi-major axis, and then you have two other orbital parameters: the inclination of how high above the ecliptic, what the tilt is of the orbit with respect to the ecliptic, which would be at 0. So you see many of these are quite highly inclined, is 30 degrees or so, and more. And then the eccentricity, which is would be 0 for something in a circular orbit, and then you can see that some of these go to very high eccentricity, and the dotted lines are the perihelion, the constant perihelion lines. So by looking at the structure in this kind of a plot, you can understand or categorize things as being affected by different resonances with respect to planets like Neptune, for example. So that's not my field, but I can appreciate how cool this really is. This is great. And then here is a sort of the poster child of that effort was a particular comet. So what on the right-hand side, this shows what I was trying to describe earlier, where this sort of loop here is a reflection of the Earth's motion around the sun, just the reflex of that. And that loop gets bigger and bigger as the thing approaches us, of course. And so this particular object was detected in DES, but then there was pre-detections which gave a longer baseline. So the number of loops here is larger than the number of seasons in DES observations. So why is this interesting? It has it turns out to be not a TNO. I mean, it is a TNO, but it's but it has a yeah. I didn't write down the the semi-major axis. But what is impressive to me is that the aphelion is 0.2 parsecs, which puts it, it has an aphelion that is, 20% of the way to the nearest star, which means that you have to account for the passage of stars in the neighborhood of the sun over this period of 3.5 million years. So it's a remarkable object. It will have its perihelion in 2031, so it's not that far away actually, and it will approach as close as 11 AU. And the fact that it's visible was detected so far out just means it has to be a very massive object, and presumably a very big object. Okay, this is actually my last slide. And I guess we're roughly on time. So I just wanted to say a little bit about, no, it's not my last slide. It's my last substantive slide. I have some ceremonial slides after this one. So just to say what we think about the legacy of the project. So obviously our papers talk about the cosmological parameters. So our papers provide a legacy, putting the cosmology aside. The high quality data allows all kinds of other things to be determined. I just showed you some good examples of that. So that's a legacy, the data are a legacy. Then the methods that we've developed for cosmology in particular, but including other things as well, that's a legacy. And then, but in some sense, maybe the most important legacy is the generation of people who've been trained using DES or working within DES on launching their careers. So they're going to go on to the next big thing. And this brings me back to Simon White's article, where he is asking the question of whether this kind of an experience of joining a gigantic project with hundreds of people working on a common effort is necessarily a good thing for people entering the field. And so that's something I will leave to you to decide, but it's something to consider. What would be the alternative? Okay, so here are the two ceremonial slides. This one is the collaboration meeting that I remember very well of a few years ago in Campinas. Sorry. I'm used to saying Campinas. And then this is the slide that tells you who is in the project from an institutional point of view. So thank you very much. Maybe we have some time for questions.
Thank you very much, Richard. Yes, thanks for the remarkable presentation. We have now some time for questions. If you joined us on YouTube, please put your question in the comment section. And if you join us here at Zoom, please raise your hand and ask your question.
I don't have a question. I just wanted to congratulate Richard. It has been a long and winding road, 15 years that we are involved in the project. And I imagine that we have still 2 years more to go, right? That's what I understood? Yeah. So you've been funded, right?
Yeah.
I do have a question. Where will the data reside after everything finishes? It will still be at the NCSA, we'll go to an NORIA lab. I mean, what is the destination of the whole data set?
Yeah, that's a very good question. So it's a question we're actually asking ourselves right now as within the project. And it's related to what are we missing by having all the data at Noir Lab? So Noir Lab has agreed to serve the public data, the DR2 and DR1. But they have not agreed to help us with our particular computing environment. So let me be more specific about that. So suppose in 2 years, we are still very scientifically active. I think that must be a true statement. And we would like to keep our computing environment to be what we've come to know and be familiar with. That would make us much more efficient, right? So if NCSA were to go away, then and NoirLab has not taken all of the files, right? They've only taken the public files that we packaged already in DR2. Then there's a problem. So we are trying to understand exactly what elements would we be missing in that event, and then finding a plan to backstop that.
What happened with this long digital sky survey data after Fermilab pulled out?
That's a good question.
It's still in Johns Hopkins, right? I mean,
Yeah, so right. It's a little invisible, right? The data are all there, but I'm not sure. I think the there would be Johns Hopkins, I think. Yeah, right. So it could be one of the national labs like Fermilab or NERSC could take this on. We don't know yet, but we understand it's a fairly urgent question.
thank you.
Yeah. Mm-hmm.
Thank you, Luis. More questions? Okay, I thought I saw someone, but
Okay, I'll take another question. I mean, is there a communication between DES and Ruben in any specific, I mean, particular desk, which is Docker and Science Collaboration?
Yeah, nothing formal. There's a lot of informal communication because so many people have joint appointments. So there are many DES people who have leadership positions in desk, for example. And so I don't think there's any fear that we're not going to understand what's happening on the other side. And there are some ideas that maybe we should, there could be benefits to being more formal about that. But we haven't done anything yet. So neither side has actually made a formal agreement with the other side. You could imagine it being helpful, right? Go ahead.
Yeah, now, and I forget his name, somebody at Berkeley, but in DESI. I just, Alzheimer's, the little German's bothering me. Sometimes I forget things. But there was a paper presenting Snowmass about actually building up data centers to actually keep all this data, cosmological surveys, let's say. I mean, DESI, DS, and is that gonna fly, or is still too soon to assess success of this idea?
Yeah, I think it's probably too soon at this point. Yeah. So the Snowmass would be just some. It's a proposal that will be discussed.
Okay.
Yeah. When I talk to the U.S. funding agencies, I hear a lot about the experiments themselves, the hardware, and not so much about the plans for data systems and the longevity of keeping these things around.
Yeah, but it also is the fact that, it's going to be getting harder and harder to move this data around. So some people were proposing to have a sort of, one single centralized data center where you would bring your code to the data rather than the other way around. Yeah.
Yeah. I don't know. I'm not very familiar with those discussions. I would have thought that LSST is so big compared to everything else that you start with whatever LSST builds, and then you just add in the small stuff inside. But I'm not sure if that makes sense. Right.
I have a question. The has collected such a huge amount of data. Yeah. Well, of course, it focused a lot on cosmology, and we have people working in this transient aspect of the data. Do you think there are maybe other aspects that are still waiting to be explored in data, maybe in stellar astrophysics, things that will be interesting to look at?
Yeah, certainly the time domain comes to mind, right? So everybody likes to to think about the value of. So DES will not be superseded by Rubin, because Rubin is to do an exquisite job of the time domain in its 10 years, but we have the data that go back, to 2012. So our data will still be valuable in the time domain for Rubin. So there's a lot of science that can be done with that. I think the DES data have not been fully explored for quasar detection and things like that. There's a very small, there is a group working on it, but it's a small group that could blossom in the future, I think, that kind of thing. So clearly there's a lot more to be done. Another way to think about that is that the number of people that I mentioned is large, but the data set is much larger than that. So in other words, there's so many opportunities for new ideas, because because of the fact that the DES collaboration has been so focused on a very particular part of the data.
And maybe there are people here with us that are not part of the collaboration. What people who are outside the collaboration can do at the moment with the data? The DR2 is public already.
Yeah, that's right. Yes. Yeah. So there's right. So if you have nothing to do with the collaboration, you can still get essentially the full data set, with the exception of some of the so for example, the photometric redshifts and the measurements of galaxy shapes, those are not yet available to the public, but they will become available in the next year or two. So then you would have everything that somebody inside the project has had access to.
But what about the single epoch measurements? Because if you're talking about time domain, I mean, you would need that, right?
Yeah, the single epoch.
Is there a plan to release that eventually?
The single epoch images are available in the public domain at NORLab. Yeah, so the single epoch catalogs are not yet. We don't yet have a plan for that. That's an interesting question. That's a good question. Yeah.
Okay, well, thanks. More questions? Okay. Well, if there are no more questions, we can now wrap this up. This presentation will be available on our website and on LIneA's YouTube channel. And we will be back with our webinar series next year on the 3rd of February with Kyle Dawson from the University of Utah, with the time still to be defined. Thank you everyone for attending, and a special thanks to Dr. Kron. Thank you very much.
Thank you.
Thank you, Richard.
All right.
Bye.
Okay. Right. Take care. Okay. Bye.
Everyone, have a great day. Stay safe, and I hope to see you all again next year. Enjoy the holiday season.
Yep. Good. Okay.
Thank you.